Hi everyone and welcome. In this video tutorial I would like to introduce a new way of doing Bayesian computations. Let us start with a classical example where we have a distribution P of z given x, the posterior distribution of z given x, as given by Bayes' formula, which is P of x given z times P of z divided by P of x. As usual, the prior distribution here is P of z, which represents the information we had about z before we started acquiring some data. And the posterior distribution is here, P of z given x, and it represents the new state of knowledge once we have observed the variable x. In general, these computations are difficult because computing P of x is not easy. This is usually intractable. And so it would be really interesting to have easier ways to analyze this kind of experiments and to learn something about the posterior distribution P of z given x. So instead of going through relatively difficult computations, a new idea is to say that we can approximate P of z given x by a new distribution. So the key idea here is to say that we're going to approximate P of z given x with a new distribution that we introduce, which is Q of z. And of course, for this to make sense, we need to choose Q that is relatively simple. Otherwise, we can go through the relatively difficult computations here. But if we choose Q to be in a class of relatively simple distributions, like the Gaussians or the Poisson distributions, for instance, then maybe we can get a good approximation to P that will have almost all the same properties as P of z given x, with much simpler calculations. Also observe that here this one of course depends on x, even though this is a distribution of z, and that our approximation here does not depend on x. This is just an approximation to the distribution of z. So if we're about to do this, we need a criterion to say that the distribution Q is somehow a good approximation to the distribution P. And the criterion that we're going to use is called the Kullback-Leibler divergence, usually written KL for Kullback-Leibler, and this is equal by definition to here this symbol Q double vertical bar P, and that is equal to the integral of the logarithm of Q of z divided by P of z given x, and everything here times Q of z dz. So this here is an expectation. Q of z is a probability distribution, so that's the expectation of that particular quantity here with respect to the distribution Qz, which I remind you is an approximation to P of z given x. So this is really nice, but the problem is that we have here in this expression P of z given x, and this is exactly what we're trying to find. So we cannot compute the Kullback-Leibler divergence here, because this would imply that we have an expression for P of z given x, and this is exactly what we're searching, so we don't have it yet. So it doesn't look like this is very useful yet, but fortunately we can work out here in this integral, we can expand it and we can make appear a new term which will allow us to find a good value here, a good distribution Q to approximate P. So here we go, we expand that integral here a little bit, and so we obtain that this is the logarithm of Q of z minus the logarithm here of P of z given x, and everything times Q of z dz. So we can use here the definition of conditional probability, and we obtain yet another expression, which is the integral of the log of q of z minus the log of p of x and z plus the log of p of x, everything times q of z dz. So here I'm using the fact that the probability of z given x is probability of z and x, or x and z, divided by the probability of x. That's the definition, and because there's a log here, I can write it this way. So this is a new expression here, and what's interesting is that p of x does not depend on z. So I can rewrite it now as the integral of the log of q of z minus the log of p of x and z, everything times q of z dz, and plus the log of p of x here. So I can take this out of the integral because this does not depend on z, and because q here is a probability distribution, it means that the integral of q of z dz is equal to 1. So here that gives me a term that comes out of the integral, and what's interesting is that this is a constant here, so that is a constant. It happens to be the denominator here of Bayes' formula, which means that this is something that's typically hard to compute. We typically do not know it, but the point is that this does not depend on z. This depends only on x, on the observations, and therefore it is not going to have any influence on whether q is a good approximation to p. So here, going back to the Kullback-Leibler divergence, if we want to find a good approximation to p, we need to have q which is such that this is approximately equal to 0. The Kullback-Leibler divergence is analogous to a distance. It so happens that this is always positive here, and that when we have q is equal to p, then that is exactly equal to 0. And vice versa. If this is equal to 0, therefore q is equal to p. So we can say that a good approximation to p is such that we minimize the Kullback-Leibler divergence. So we're going to find the q here in this expression that minimizes the Kullback-Leibler divergence. And this is exactly the same as minimizing this expression, which is here, because that's the one here that depends on q and on z. This does not depend neither on q nor on z, so it does contribute to the value of the Kullback-Leibler divergence, but this does not influence which distribution here, q, minimizes this. So we want to minimize this expression here. If we can find the value of q that minimizes this expression, then this particular q will be the best possible approximation to p that we can give. And so when we look at the terms that are here, what do we have? We have the log of q of z. Because we're going to choose q the way we want in a class of function that we want, for example the Gaussians or the Poisson, then we can choose something simple that we can compute here. P of x and z is the numerator of the Bayes formula here. This is something that we can typically compute. This is called the model, actually. So this says how z and x depend on each other, but more importantly, the fact that probability of x given z is pretty much always known because we assume that it has a certain distribution. And p of z is our information about z in the beginning, so we know this. So this we can choose and we can make it simple. This we know, this is the model. And finally, we have the term q of z here, which means that we need to compute the expectation of this particular term here over our proposed approximation. So this is something that has a chance of being much simpler to compute than this term here, and especially the numerator p of x that is here. So one interesting thing about this expression is the fact that this here is positive. So it's just because the Kullback-Leibler divergence is always positive. This is a mathematical fact. So now if we re-express this in a slightly different way, we find that the logarithm of p of x, which is called the logarithm of the evidence, the denominator here of base formula is called the evidence, is always greater than this particular expression, which is the one that I wrote here with a minus sign. And I'm going to just swap the terms around, which means that this is equal to log p of xz times q of z dz minus the integral of log of q of z times q of z dz. And that here is called the ELBO, ELBO. So that is the ELBO. And this stands for evidence lower bound, because this is here on the left hand side, this is the evidence, and this here is a lower bound, as you can see here, for the evidence. The evidence is always above that particular value here. So that here is called the ELBO, and we need to maximize it. We need to find a distribution q of z such that the ELBO is as big as possible. So if we can find the value of q here that maximizes this expression, then we have the best possible approximation to the posterior distribution here. So to recap, instead of computing this difficult expression here through the difficult denominator that is here, we can choose a class of distribution. We can choose a certain value, a certain class of distributions for q to be in, and then compute this much simpler expression that is here. We'll see in a minute why this is simpler, and then find a maximum to that expression in order to get a good approximation to the posterior distribution that is there. And hopefully this approximation will have almost the same properties as the original p of z given x. A graphical way to think about it is to say that we're going to say that the distribution q is within a certain set here. So that'll be the set that we consider, the set of possible q distributions. The true posterior distribution here, p of z given x, is somewhere in the search space, and what we're after is the closest point here within that search set to the target distribution, which is here. And we're going to say that here the distance that we use is the Kullback-Leibler divergence. So we're going to start in a particular point here in the set of q's, and then we're going to try and find a way to get as close as possible to that particular point here, which gives us the best q within the search space that is there. And then we will never really get for sure to the true posterior distribution, p of z given x, but within the constraints that we give ourselves, within the complexity that we're ready to spend to find a good approximation to p, with a bit of luck, we'll be able to find the q here that is the closest to the target P of Z given X. We are going to give an example with Gaussian distributions to make it more concrete, but first let's review something that will be quite useful about Gaussian distributions. So if we have a distribution X which has a Gaussian distribution with parameters mu here and sigma squared, we are interested in the value of the expected value of x squared. So to compute this, we can remember that kind of by definition, the variance of x is equal to the expected value of x squared here minus the expected value of x everything squared. So with this, we can now go back to expected value of x squared and say that this is equal to the variance of x plus the expected value of x everything squared. And so we happen to know these values. The first is that the variance of x is sigma squared. This is by definition here of the Gaussian distribution. And the expected value of x is mu, which means that the expected value of x squared is mu squared. So it's kind of interesting that we have here for a Gaussian distribution, the expected value of x squared is sigma squared plus mu squared when the parameters are mu and sigma squared. So this is something that we don't really need for now, but I wanted just to make a little bit of a reminder about this because we will need it for later. So now we're going to consider a case where we have a variable mu here that will be drawn from a Gaussian distribution and with parameters a and b squared. So that's a case that we have worked out in another video, so we know exactly what to expect here. So first we draw a variable mu from a Gaussian distribution, and the parameters a and b are supposed to be known before we start. Once we've done this, we now use mu to draw new variables here, x, such that the expected value of these variables is mu here, and the standard deviation is sigma. And again, sigma is assumed to be known here. So we observe a couple of x1, etc. until xn, and we are interested in the distribution of mu given the observations x1 to xn. So our target here is f of mu given x1, etc. till xn. And we know the solution here. We have computed this manually in another video, so this will be interesting to compare what we obtain when we use the ELBO method to compute the posterior distribution of mu given x1 to xn. So to start, I observe that this here that I wrote f of mu given x1 to xn is the true posterior distribution of mu given the x1 to xn here. And I need to approximate it. So the way I'm doing this is that I'm saying that I'm defining a new variable here, a new density of probability q of the variable mu here, and we want this to be a good approximation for the true but unknown posterior distribution which is here. And what we're going to say is that this is a Gaussian. So this is where we're taking a leap of faith. We say that we're going to search for that particular approximation here within the set of Gaussian distributions. And so how do you define a Gaussian distribution? You need two parameters. So the first is the expected value, and I need to introduce yet another parameter, so I'm going to call it xi here, the Greek letter xi, and I don't know what xi is. I just know that I'm going to look for the best xi here so that I can approximate this f here with a Gaussian distribution. And the standard deviation is going to be equal to kappa, this other Greek letter here. So I'm saying that I'm ready to search for a good approximation to the true posterior distribution here within the Gaussian distributions. And so I have now transformed the problem into finding the best xi and the best kappa. If I have that, then I have solved the problem and I have found the best approximation Q within this family, of course, to the target distribution here, which will remain unknown to me. So to do this, I need to start with the definition of the ELBO, which we obtained previously, and this is what I will have to maximize. So by definition here, remember, the ELBO is equal to the integral of log of p of x comma z. I'm going to keep the same nomenclature as last time, times q of z dz, and I will change it in a minute, minus the integral of the log of q of z dz. In reality, I don't have a z here in this problem, and I don't have a p. I have things that I've written f, and I still have my q here. And so I'm now going to replace the old letters here by the new symbols that I have for this specific problem. So this is equal to the integral of the logarithm of f of mu, this is the prior distribution of mu here, times f of x1, etc. until xn given mu. This is the full density for observing x and z here, which is all the x's and mu, times q of mu d mu. So mu is the integration variable here, minus the second term, which is integral of the log of q of mu times q of mu d mu. And so we have a first part here, like a term number 1 and a term number 2 here to compute the ELBO. And so we're going to compute them separately. So for this, we need to remember how to express the particular Gaussian distribution. So we're going to start with term number 1 here. And so here we go. The term number 1 here, the most important part is to be able to express the logarithm of this particular density function here. So we have the log of f of mu here. So this is the log of the prior distribution plus the log of f of x1 till xn given mu, which is the model that we have. So we have to start with this. And remember that because mu is Gaussian here and the xi are Gaussian, so we have an expression of the form, the generic form here, for example, for the x is that f of x given mu is by definition 1 over sigma square root 2 pi times the exponential of minus 1/2 x minus mu divided by sigma, and all this squared here. So this is the definition of the Gaussian distribution for that particular case. And remember that mu is also has a Gaussian distribution, so it will have the same form. So when we take the log, there is some term here that we won't really care about, and we will have something here that will be an expression, a polynomial of degree 2 that appears here. So going back now to log of f of mu, I obtain some constant here that does not depend on mu, and I'm going to again use this capitals here just to say that I don't really care about these values here. And so that will take care of the normalization constant here for the expression of mu, minus 1/2. So now I'm writing this bit here, and in the case of mu, this is mu minus its expected value, which is a, divided by the standard deviation, which is b in this case, and everything is squared. So that's here for the first term. You see that this is fairly simple. And what about the other terms? I have n terms that look fairly similar, and so they all have this normalization constant in front here that I don't care about one more time because it does not depend on mu. It doesn't have anything interesting for me, so I will just pack them into this constant c here. This cannot have some influence about mu, and so I'm continuing the terms. So I obtain minus 1/2, and this time I have x1 minus mu divided by sigma, and everything here is squared. And I have n terms like this that are similar. They have the same form here. So the last one is xn minus mu divided by sigma square here. So this is what we have here inside this part of the integral here. It looks like this. So that's part number 1. And so from here it's easy to get confused because we have a lot of terms that appear and they're coming from different sources. But remember that by definition, when we compute the ELBO here, we are doing the integration over the distribution here, Q. So we're taking the expectation as if mu here was truly coming from that distribution, not from the other distributions. We're really saying that we're going to take the expectation of that value here, which we have computed as that, over this particular distribution, the one that we're trying to find. So we're going to assume that mu is distributed as here a Gaussian distribution with parameters psi and kappa. And so having that assumption, now this means that mu minus a is distributed as a Gaussian here with parameters psi minus a and kappa. Okay, when we remove the constant here a from the variable mu, then it just shifts the expected value by a. And likewise, the distribution of mu minus xi is a Gaussian with parameters psi minus xi and kappa here. And so because we have computed the value of the expected value of x squared when x is Gaussian, we are now able to compute the value here of this term when we take the expectation over mu having these particular distributions. And so what we obtain is that this is c minus 1/2, and so now this is a Gaussian of this form, so we have psi minus a squared plus kappa squared. This is the expected value raised to the power 2 plus the variance here. And the term b squared remains here, so we keep it. And the other terms, we get minus 1/2. So this one here, it's written x1 minus mu, but because it's squared, it's the same as mu minus x1. And so we have a term that's equal to psi minus x1 squared plus kappa squared. And this is divided by sigma squared. And we have n terms equal to this one here. So this is it. We now have an expression for the term number 1 that is here. It's equal to that particular sum that's here. There is this constant that we don't care about because it has nothing to do with mu, so we keep it as a c. And we're also going to compute now the term number 2, and it's going to be using the same exact logic that we have here. So number 2 here is equal to log of q of mu So in this case, when I write the log of q of mu, I need to write it entirely specifically. Why is that? Is because q here depends on psi and kappa, which are the two parameters that I'm interested in finding. So I write it entirely, which is minus log of kappa minus 1/2 log of 2 pi minus 1/2 mu minus the expected value, which is psi, divided by the standard deviation, kappa, and everything squared here. So, as above here, I assume that mu is distributed like a Gaussian distribution with these parameters here, which means that mu minus psi has a Gaussian distribution with expected value 0 here, because I remove the expected value, and standard deviation kappa. So when I take the expected value now of that particular term, here only mu will be replaced, then I obtain the full expression, which is as follows: minus log of kappa minus 1/2 log of 2 pi. So this here is an irrelevant constant. It doesn't change at all the value that we obtain, but kappa does. So this is why I needed to write the expression here in full. And now when I take the expected value of this new random variable, I obtain 0 squared plus kappa squared divided by kappa squared. And so that here, which is here, is an irrelevant constant. That is equal to 1 here, and that is equal to minus 1/2 log of 2 pi. That has no influence on the calculations whatsoever. So the only term I need to keep for the term 2 is minus log of kappa here. So in the end, what I obtain is from the term number 1, I have this here, which I need to keep, and from term number 2, I have that. So this says that in the end, the ELBO is term 1 minus term 2, and we obtain that this is equal to that term which is here, so minus 1/2. Here I'm going to factorize with the minus 1/2, and so xi minus a squared divided by b squared plus xi minus x1 squared divided by sigma squared, and I have n terms like this, so the last one is xi minus xn squared divided by sigma squared, and finally I have the terms in kappa squared that are here, so I have 1 kappa squared divided by b squared here, plus n terms kappa squared like this, so n times kappa squared divided by sigma squared. So that's what I got here from term number 1, and minus term number 2, this is plus log of kappa here. So that's the ELBO, and this is what I have to maximize. And so what are the parameters that I need to play with is xi here, xi. So what are the parameters that I have to play with? This is xi here, which appears multiple times, and kappa. So how do I find the maximum of the ELBO with respect to xi and kappa? Well, one thing that I can do is I can just compute the derivative of the ELBO with respect to xi and kappa and see how I can make this derivative equal to 0. This is the standard way that you can find the maximum of a function. So here we go. We start with, we're going to write the derivative of the ELBO with respect to xi is, so minus 1/2 here, and so what do we have? The first term is xi minus a here, so when I do the derivative with respect to xi, it gives me that, divided by b squared. And the other terms are going to be similar, so I obtain xi minus x1 divided by sigma squared, and I have n terms that are like this one, until xi minus n divided by sigma squared. And this does not depend on xi, so that's it. I am done. And now this here has to be equal to 0 for the ELBO to be maximal. And so we just need to find the value of xi such that this is equal to 0. So here we go, we continue the derivation. And this -1/2 here becomes irrelevant because this is a product of -1/2 with something, so that something here has to be equal to 0. And if I collect the terms with respect to xi, I obtain xi times 1 over b squared plus n times 1 over sigma squared. This is the collection for the xi here, and the rest of the terms are minus a over b squared here plus x1 plus until xn divided by sigma squared. And that here is equal to 0. So in the end, the solution is that xi is equal to this divided by that. So here we go. So this is a squared, a divided by b squared plus here x1 plus all the terms until xn divided by sigma squared, and everything divided by 1 over b squared plus n divided by sigma squared. So now this, I can multiply here by sigma square on the numerator and the denominator, and what I obtain is xi is equal to a times sigma square over b squared plus x1 plus xn divided by sigma squared over b squared plus n. So this is the value of xi here. So at the end of these computations, we obtain that the best Q that we can find here among the Gaussian distributions is such that the expected value should be that. And so this is exactly the term that we obtained when we went through the direct computation. So that's exactly identical. Let's move on and see what happens for the second parameter, for kappa. So we differentiate the ELBO with respect to kappa, and we obtain that this bit here does not depend on kappa at all. So what we obtain is -1/2. And here we have 2 kappa divided by b squared. And here we obtain 2n kappa divided by sigma squared. And that log k here gives 1 log kappa, 1 over kappa. And that here has to be equal to 0. So we're going to do a little bit of algebra here So first of all, this 2 and 1/2 cancel out, and I'm going to put everything here to multiply everything by kappa. So I obtain kappa squared divided by b squared plus n kappa squared divided by sigma here is equal to 1. So I shuffled things around, I multiplied everything by kappa, and I put this on the other side so that I end up with that. So now this is equivalent to kappa squared times 1 over b squared plus n over sigma squared is equal to 1, or kappa squared is equal to 1 over b squared plus n over sigma 2. And if I multiply everything by sigma squared at the numerator and the denominator, I obtain sigma squared divided by sigma squared over b squared plus n. And so here, this is the value of kappa that we obtained with that method. So this is yet again the same value that we obtained with the direct calculation method. So the new variance that we obtain in the approximation of the posterior distribution is the same as the true variance of the posterior distribution. Our approximation is actually spot on. So let's recap. Q now of mu is the Gaussian distribution with parameters. The average is this term which is here. So this is A times sigma squared divided by b squared plus the sum of all the xi divided by sigma squared divided by b squared plus n. And the variance is here, so this is sigma squared divided by sigma squared over b squared plus n. And so this is exactly the same result as we obtained when we used the direct approach. So why is it exactly the same result? Well, it's because we have looked for Q here in the class of functions that are Gaussian. And as we had established with the direct method, it happens that the posterior distribution, the true posterior distribution of mu given the xi, is Gaussian. So when we're looking for a solution which is in our search space, then we find it, and we find it exactly. So going back to the graphical example that we had before, so if the search space is something like this, so that's the set where we're looking for the Q here, and if the optimal here, the true posterior distribution, is inside the set Q, then I can find a way here that gives me exactly there. So the distribution that I find in the end for the posterior distribution of z given x is exact. In that particular case, if the solution is within the set that I'm looking for, then I find it. So this is the beauty of this approach, is that when we are looking for the solution in the set that contains it, then we find it. The problem is that we never know whether this is the case. Well, not never, because in this case we were able to go with a direct computation, but in general you do not know whether you are in this case here, where the true target distribution is within the search set, or whether it's outside, and then you will have to stay within the search set and you can only approximate it, but do not really find the exact solution. So the main advantage of this method is that it is actually relatively simpler than the difficult computations of the Bayesian formula. It doesn't look like this in this particular example because for the Gaussian distribution, the Bayesian formula is, the Bayes formula is actually straightforward. So the main advantage of this method, of the ELBO method, is that the computations are in general easier to perform than the ones that use Bayes formula. In the case of the Gaussian distribution, they have approximately the same level of difficulty. But in many other cases, it's much simpler to go through the ELBO method than through the direct Bayes calculation. The second advantage of this method is that if the posterior distribution is within the set that we're searching, then we find it. So we can get the exact solution with this method. There is a third advantage to this method, which is not going to appear until later. But if we go back to the definition here of the ELBO, it appears to be an integral here. And this integral is very often difficult to compute. We say that this is intractable. But on the other hand, we can approximate it using Monte Carlo method. Because Q here is a distribution that we choose, then we can choose a distribution that's easy to sample from. And we'll see that this allows us to compute an approximation of the ELBO using Monte Carlo method that works pretty much all the time. So this is the main advantage of this method, but we will see later how this plays out, is the fact that you can almost always use it and you get something out of it, contrary to the typical Bayesian calculations, which are often too difficult. Now, the main disadvantage of the method is, of course, that this is an approximation. And worse than this, you never really know how far you are from the true posterior distribution. You can always think that you get the best possible approximation within the set that you're searching, but in general, you don't know how far you're going to end up compared to the true distribution. So you don't have any guarantee whatsoever that your solution is even remotely similar to the true posterior distribution. So that's a real big problem to keep in mind when using the ELBO method. That's it for this video. Thank you for listening and see you soon.